From the smallest grains of sand to the most distant stars, everything we see around us is made of matter. But what is matter made of? The answer lies in the realm of the very small, in the heart of atoms, where we find quarks. Quarks are fundamental particles combining to create protons and neutrons in every atom. Understanding quarks unravels the mysteries of the universe, from the forces that govern matter to the processes that fuel stars. Quarks are the Lego bricks of the subatomic world. Their discovery revolutionized particle physics, leading to profound insights into the nature of matter. The world of quarks is surprisingly diverse. There are 6 different types or flavors of quarks: up, down, charm, strange, top, and bottom. These whimsical names, coined by physicists with a sense of humor, belie the profound implications of these particles. Each quark flavor possesses a unique set of properties that determine its behavior and interactions. These properties include mass, electric charge, and a property called spin, which we'll explore later. The 6 quarks can be grouped into 3 pairs or generations based on their mass and other characteristics. The up and down quarks are the lightest and most stable. They are the constituents of protons and neutrons, the familiar particles found in the nucleus of every atom. The charm and strange quarks are heavier and more exotic. They are produced in high-energy collisions, such as those that occur in particle accelerators. The top and bottom quarks are the heaviest of all. They are extremely short-lived and decay rapidly into other particles. The top quark in particular is so massive that it took decades for physicists to confirm its existence. Protons and neutrons, the building blocks of atomic nuclei, are not fundamental particles themselves, but are composed of quarks. A proton is made up of 2 up quarks and 1 down quark, while a neutron consists of 1 up quark and 2 down quarks. The electric charges of the quarks determine the overall charge of the proton and neutron. Since the up quark has a charge of +2/3 and the down quark has a charge of -1/3, the proton has a net charge of +1, while the neutron has a net charge of 0. The quarks within a proton or neutron are held together by an incredibly strong force, aptly named the strong force. This force is mediated by particles called gluons, which act like glue, binding the quarks together. The arrangement of quarks within protons and neutrons is not random. They are constantly in motion, buzzing around each other at incredible speeds. However, the strong force keeps them confined within the nucleus, preventing them from flying apart. Quarks possess 2 fundamental properties that distinguish them from other subatomic particles: electric charge and spin. We've already touched upon electric charge, which determines how particles interact with electromagnetic fields. Spin, on the other hand, is a bit more abstract. Spin is an intrinsic angular momentum that all fundamental particles possess. It's not quite accurate to think of quarks as tiny spinning balls, but the analogy helps to visualize the concept. Spin is quantized, meaning it can only take on specific discrete values. Quarks, like electrons, have a spin of 1/2. The spin of quarks plays a crucial role in determining the properties of composite particles like protons and neutrons. For example, the spins of the quarks within a proton all align in the same direction, giving the proton an overall spin of 1/2. This spin alignment contributes to the magnetic properties of protons and neutrons. Section 5, the force that binds color charge and the strong force. The strong force binds quarks within protons and neutrons. This force works through a property called color charge. Unlike electric charge, color charge has 3 types: red, green, and blue. Opposite color charges attract each other. A color-neutral object must have all 3 colors equally. Quarks combine in groups of 3 or in quark-antiquark pairs to form color-neutral particles. Section 6. Beyond up and down, unveiling the heavier quarks. While up and down quarks are the most common and make up the familiar protons and neutrons, the other 4 flavors, charm, strange, top, and bottom, are no less important in understanding the universe. These heavier quarks are produced in high-energy environments, such as those found in particle accelerators or in the early universe. The discovery of heavier quarks began in the 1960s with the observation of particles containing strange quarks. Charm quarks followed in the 1970s, and the bottom quark was discovered in 1977. The top quark, the heaviest of all, proved to be elusive and was finally discovered in 1995. These heavier quarks are all unstable and decay rapidly into lighter quarks and other particles. However, their brief existence provides valuable insights into the nature of the strong force and the fundamental symmetries of the universe. Their properties have also helped to confirm and refine the standard model of particle physics, our current best description of the fundamental particles and forces. Section 7. Quarks and the Cosmos, a Universal Influence. Quarks might seem like esoteric particles confined to the realm of the very small. However, their influence extends far beyond the atomic nucleus. Quarks play a crucial role in the structure and evolution of the universe, from the cores of stars to the cosmic microwave background radiation. In the extreme heat and pressure of the early universe, quarks roamed freely in a sea of energy. As the universe cooled, quarks combined to form protons and neutrons, which then assembled into the first atomic nuclei. This process, known as Big Bang nucleosynthesis, laid the foundation for the formation of stars and galaxies. Inside stars, nuclear fusion reactions powered the stellar engine, converting hydrogen into helium and releasing vast amounts of energy. These reactions involve the strong force and the interactions between quarks. Without quarks, stars as we know them would not exist. The study of quarks also provides insights into exotic objects like neutron stars and quark stars. Neutron stars are incredibly dense remnants of massive stars, composed primarily of neutrons. Quark stars, hypothetical objects even denser than neutron stars, are thought to be composed of a soup of free quarks. Section 8. The future of quark exploration. The discovery of quarks has revolutionized our understanding of the universe. Particle physicists continue to explore the properties of quarks and the strong force. Experiments at particle accelerators like the Large Hadron Collider probe the limits of our knowledge. One major mystery is the origin of quark mass. The Higgs boson, discovered in 2012, is thought to give mass to fundamental particles. Another area of research is physics beyond the standard model. Some theories predict additional, heavier quarks. The exploration of quarks is a journey into the heart of matter.